Our project is about a hybrid fault detection and correction AES for space application. Our aim is to detect and correct fault during transmission of data in AES algorithm. This is our block diagram, in which we can see that we are giving 128-bit input and 128-bit key into the encryption block, and the output will be 128 bits. The 128 bits will be passed over to the Hamming encoder, where the data is encoded with parity bits. Now the result will be 192 bits, which will be transmitted to Hamming decoder, where it will be decoded and the error is detected and corrected, and the output will be 128 bits, which is passed over to the decryption block, where the decryption takes place and the plain text of 128-bit output is got. Now we will be seeing these processing models in software. Now we'll be setting the clock. Now we will be setting the reset. We will be giving the reset as 0. Now we will be setting the LD as 0. Now we will be given a 128-bit key. This is our key. Now we will be giving the input 128 bit. This is the input. This is the output for reset and LD as 0, and now we will be resetting it as 1. And we will be assigning LD as 1. Now we simulated it for our reset and LD as 1. Now we have done for LD as 0 and reset as 1, and we are running the process for 12 times. These are the 10 steps of key generation as well as the ciphertext generation. Since we are using 128 bit as input, there are 10 rounds of ciphertext generation, and we can see those 10 steps here. These are the steps for encryption. These are the things we have performed now. Now the output will be got for the third round, that is reset is 1 and LD is 0, and we will be simulating it till we get done bit as 1. This simulation includes the starting we have given the plain text, that's 128 bit, which will be added to a key which we have given it as 128 bits, and the following processes happen. These are the steps. Since we are using 128 bits, we have 10 rounds of key generation, and these are the steps. This includes the 4 steps, that is sub bytes, shift row, mix column, add round key. And in the last step we will be seeing that only sub byte, shift row and add round key will be performed. These are the steps in key generation. Now the output will be given to Hamming encoding for the fault detection as well as the correction. We are just performing first Hamming encoding before the transmission, because we are going to detect as well as correct the error during the transmission process only. Now, as we did an encryption process, we perform the Hamming encoding, and the output is this. In the Hamming encoding, we will be adding 4 parity bits, which will be recovered in the Hamming decoder after the transmission, and we will be generating new parity bits with the input, and we will be comparing it with the received parity bits, and we will be finding out the error and its position of the error. After the Hamming decoding, we will be doing the decryption process, in which the reverse process of the encryption processes will take place, which consists of inverse shift row, inverse byte substitution, inverse mix column, and inverse add round key. This is the block diagram for decryption process. This is the output for Hamming decoding. After the transmission, we will be performing this. In this, we can find out the error also. Now we will be performing the decryption process. As in the case of same process of encryption, we are performing this also, and the output will be displayed like this. This is the end of our project. There are many applications for this project, that is mobile banking, ATMs, satellite communication, military application, etc. Wherever we are using the wireless transmission, we need this technique for the error correction as well as the detection. The main aim of our project is to detect and correct the single event upset errors. These are the outputs. That's all.